Alright, so today we're going to talk about inverse relations, and then we're going to go into inverse functions. So, to start with, let's remember what a relation is. A relation is a set of ordered pairs. You have inputs and outputs. So, let's suppose that I start with a relation, and I will put the inputs and outputs in a table format. So let's say I have an input of -2 partnered with an output of 0. An input of -1 with an output of -3. An input of 0 with an output of -4. An input of 1 with an output of -3. And an input of 2 with an output of 0. So that represents a relation. It's a set of ordered pairs. So over here, we want to leave some space in the middle for a graph. And over here, I'm going to talk about the inverse relation. So in an inverse relation, the input and the output are switched. So I would input a 0 and get out a -2. I would input the -3 and get out a -1. Input a -4, get out a 0. Input a -3, get out a 1. Input a 0, get out a 2. So watch what happens if I compose two inverse relations. I put in a -2, get out a 0. Take this 0 and put it as the input here, and I get out a -2, back to where I started. Can do that with each pair, right? So we think about things in life that would operate as inverse relations, like pressing fast forward for 27 seconds and then pressing rewind for 27 seconds. You get back to where you started, right? There's the idea behind inverse relations. They undo each other. The input and the output are reversed. Alright, so now let's look at what happens to them graphically. So I'm going to draw a coordinate plane, x, y. I'm going to graph my relation in blue, and then I'm going to graph the inverse relation in red. So if you have a different color for your inverse relation, it might help you see what's going on. So I'm going to plot -2, 0, and I'm going to plot -1 with -3, and I'm going to plot 0 with -4, and 1 with -3, and then 2 with 0. So my first relation graphs as a parabola. Alright, now I'm going to graph the ordered pairs for my inverse. So my inverse is at 0, -2, -3, -1, -4, 0, -3, +1, and then 0, +2. My inverse relation is a parabola that is opening to the right. Now, on this graph, I'm going to come draw a very special line. I'm going to draw a line that goes through 0, 0 and has a slope of 1. So it has a positive slope. It's going to go through 1, 1, 2, 2, 3, 3, negative 1, negative 1, and so on. And so this is the line y equals x. If you think of y equals mx plus b, the slope is 1, the y-intercept is 0. All inverses reflect over y equals x. So think about it, what it means to reflect. So do you see that if I were to fold on this dotted line here? You see that if I folded it, and the red here would fold over on top of the blue? Can you see, maybe if you just look at it in pieces, can you see how this piece here would fold over this piece? Look, when you look at it like that, doesn't it almost make a heart between the two of them, kind of? Appropriate for Valentine's Day. See the reflection? That is true of all relations. Well, doesn't that make sense? If the x and the y, the input and the output, are flipping, and this is the line y equals x, then they're going to reflect over that line. All right. So relations have inverses. The x and the y trade places. The inverses reflect over y equals x graphically. But then we want to go further, and we want to question if a relation is a function, is the inverse relation a function? That's our question. And it's not just a yes or no question. It depends. Sometimes the inverse relation is a function, and sometimes it's not. So there's going to be an inverse relation, but it may or may not be a function. All right, so let's look at our relation that we started with. Do we agree that this is a function? No two different ordered pairs have the same first element. Look at your blue graph. Does it pass the vertical line test? Yes, it does. Well, what about our red relation? Is it a function? No. Do you see these two different ordered pairs? They have the same first element. Look at your graph. Does the red graph pass the vertical line test? No. So in this case, the inverse above is not a function. So the relation can have an inverse, but the inverse may or may not be a function. So there's some ways that you can know without graphing the whole thing. So remember, a relation is a function if it passes the vertical line test. So if the original relation passes a horizontal line test, right? So we're switching it from vertical to horizontal. So if the original relation passes a horizontal line test, then the inverse relation will be a function. So let's take a minute and go back up to our blue graph here. So let's say I didn't even graph the red one. I'm just looking at the blue one, and I'm wondering, would the inverse of this be a function? So if I take this blue graph, and instead of drawing a vertical line, I draw a horizontal line, and my horizontal line crosses in two places, then I know the inverse is not a function, because the inverse would in turn fail the vertical line test. Okay? All right. If we do have two functions, there is an interesting thing that relates the domain and the range. So if I have a function, f of x, and then I have the inverse function. So just remember, this is our notation, this little -1 here, this denotes inverse function. Do you remember that from trigonometry? When we had inverse sine and inverse cosine, those buttons on the calculator. So this is f inverse of x. That's what that little -1 means. So the domain of my original function matches the range of my inverse function. And then my range of my original function is going to match with the domain of the inverse function. Well, that makes sense again, because the x and the y, the input and the output, are switching. So domain and range, domain, they're going to switch. But this becomes really important because remember, sometimes we have restricted domains. So we have functions that are only functions under a restricted domain. So if a domain or a range is restricted, then when you do the inverse, the range and the domain are going to be restricted the other way. All right? Okay, now let's move on to the next part, which is how we find an inverse algebraically. So, table, easy, just flip the x and y. Graphically, reflect over the line y equals x. Now we're going to look at finding an inverse algebraically. Find the inverse algebraically. Algebraically, using algebra. So I'm going to do an example, but as I do the example, I'm going to write steps to the side. So let's say we have f of x equals the square root of x minus 4. All right, so step 1 is going to be to write in terms of y. So I'm going to back away from function notation, and I'm going to write this as y equals the square root of x minus 4. Alright, and then I am going to write the inverse. So normally when we work with equations, everything that we write is equal to the line above it. Well, now I'm going to write something that's not equal to the line above it. So now I'm going to write the inverse. And the way I'm going to do that is I'm going to swap the x and y. And so once I make that swap, I'm not writing the same equation that's up here. Now I'm writing the inverse. So it's going to be x equals the square root of y minus 4. So I've taken x and y, traded positions. Now, the next thing I'm going to do, which might take me several steps, is I am going to solve for y. So in this case, if I want to get this y by itself, I need to eliminate my square root. So how do I undo a square root? I square it. So I'm going to take what I have here, exactly as written, and I'm going to square both sides of my equation. Square this side and square this side. So my left side is going to become x squared. And on my right side, my square root and my squaring undo each other. And now I have y minus 4. Alright, again, my goal is to get y by itself. So now we'll add 4 to both sides. And now we'll have y equals x squared plus 4, or x squared plus 4 equals y. So now I have solved for y, right? All of this process right here was solving for y. And so then the last thing that I do is I write in function notation. So this y is not the same y that I had up here. This y is f inverse of x. So I'm going to write f inverse of x equals x squared plus 4. All right, now let's talk about the domain and range of each of these. All right, so let me go back up to my original function. What would happen if I put a 4 in for x? 4 minus 4 is 0. What's the square root of 0? Try it on your calculator. I saw some of you shake your head like, I don't think we can do that. But we can, right? You can take the square root of 0. The square root of 0 is 0. That's fine. But what if this x was a 3? What if I had 3 minus 4? That would be negative 1. What's the square root of negative 1? What happens there? Non-real answers. So it's not that there's not an answer, it's just not a real answer. It's going to be an imaginary number. Remember imaginary numbers? We'll talk more about those next week. But for right now, we're in the real number system. So I can't take the square root of a negative in the real number system. So therefore, I have a limit on what my x values can be, right? My x values have to be greater than or equal to 4. Alright, so when I'm dealing with a square root, x minus 4 has to be greater than or equal to 0. I can take the square root of 0, but I can't take the square root of negative numbers in the real number system. So then if I add 4 to both sides, that's how I get that result. X has to be greater than or equal to 4. Or if I were to write that in interval notation, my domain would have to go from 4 with a bracket up to infinity. All right, what about my range for this function? If I take the square root of 4, I know I'm going to get 0. Is my square root ever going to come out negative? So you see that your range is going to be all y's greater than or equal to 0, or 0 to infinity, like that. Alright, so now here's what that means. If this is my domain and range for my input, for my function, then my inverse function down here, the domain is going to be equal to this range. So my domain is only going to go from 0 to infinity. And my range is going to be 4 to infinity. So the domain and range for my function become the domain and range flip for my inverse.